Houston, this is Shuttle 2.
Oh, Shuttle 2.
We have final data on our orbit here. Looks like apogee and perigee are within 0.1 of what we planned.
Raj, can't do much better than that.
And we've got the Earth observation R&D package all checked out and ready to go.
Roger, Al. How about giving us a TV picture at your convenience?
Roger. John says it should be on now. And the cargo bay is coming open. Mark, cargo bay doors open all the way. And we're deploying the Earth observation package.
We've got greens all here, Al.
Roger that, Houston. John's checking the systems here and says it all looks good. Okay, she's out all the way. Lock. Okay, and I'm rolling to viewing attitude. Here we go. Okay, there we are. George and Bob are looking out the optical tracker.
And what of you?
Okay, we're coming up on Phoenix, zooming in on Sun City, and you can see the two golf course greens clear as day.
This is not a science fiction movie. This is a computer simulation of the future of the United States in space. The vehicle is called the Space Shuttle, an airliner-like spacecraft capable of over 100 trips from Earth into Earth orbit. This mission is called a sortie mission, wherein the Space Shuttle is used as an independent orbiting laboratory. Missions of this type would be early steps in the utilization of space in near-Earth orbit. The flexibility of the shuttle can be used to carry out many missions, especially in the fields of astronomy, physics, communications, navigation, and to obtain data on slowly varying phenomena such as natural resource deposits. A further step would be the construction of an orbiting space station to provide a long-term applications, experiments, and observation platform to look inward toward Earth and outward toward the universe. The space station and space shuttle are two key and integral parts of our future in space. Already, programs are underway studying the hard realities of such a system. At Houston's Manned Spacecraft Center, for instance, a hybrid computer-driven simulation system is being used to study the characteristics of the proposed shuttle and station configurations. On one side of the screen is an out-the-window view taken during the Apollo 14 landing. On the other, a simulation run using this equipment to simulate a lunar landing early in the Apollo program. It was comparatively simple to convert this equipment to help work out the far less complex problems involving the space shuttle and space station, which will operate in orbits in the vicinity of only 270 miles from Earth. Today, an evaluation engineer uses the same equipment to fly rendezvous or Earth landings from a space shuttle cockpit mock-up with the same computers providing dynamic engineering data and generating the visual image. We have already had a glimpse of how a shuttle sortie mission would work. Now let's take a look at how the shuttle would function in the construction of a space station. The animation you will see is not from an artist's drawing board, but is an accurate computer simulation. It was done on a computer similar to the one used for the pilot simulator, but which has a more detailed program. The orbiter stage of the shuttle has been launched from Earth into a near-Earth orbit of about 270 nautical miles. A manipulator is used to extract the space station core module from the cargo bay. These deployment operations using the manipulator will take about 12 to 15 minutes. The core module is the first section of the space station to which subsequent modules will be attached. Ports are arranged so that end berthing or side berthing can be accomplished. Once the core module is in proper attitude, the shuttle orbiter will return to Earth. The next shuttle mission, a few days later, will rendezvous with the core module in preparation for attaching the next section, the electrical power module. It should be noted that this shuttle is an earlier design used for this analysis. The crew uses the manipulator to take a berthing adapter from the cargo bay and attach it to the shuttle. The manipulator is then used to capture the core module and rotate it to the correct attitude. The core module is berthed with the shuttle at the adapter using one of the side ports. This berthing is done to keep the station steady while new modules are attached. The electrical power module is taken from the cargo bay and maneuvered to a berth with the core module at one of the core module's end ports. The electrical power module consists of two assemblies, a power boom and a solar array, which is retracted during this phase. The station is then released from the side berthing position and rotated to position for end berthing with the adapter. The station is then left in orbit, with the adapter attached for dockings with subsequent shuttle flights. The shuttle then returns to Earth. In this configuration, the station's electric power needs are minimal and it is effectively inert. The third mission will attach the third module, known as Station Module 1. Using the berthing adapter, the shuttle once more berths with the station prior to attachment of Station Module 1. The manipulator is used to unload the station module and soft dock it to the core. This will in all probability be a crew control center module. The station modules differ from the core and electrical power modules, but each station module to be attached, regardless of its function, is built on basically the same structural layout. Each module can then be outfitted on Earth to fulfill its individual function. The solar array booms are then unfolded and the solar cell panels deployed. During this phase, a complete checkout is performed from the station control center. The solar panels cover an area of 7,000 square feet and produce an average of 19,600 watts of continuous condition power. Fuel cells and power storage facilities are also contained within the station for normal operation during the night portion of each orbit. The station is then detached from the shuttle and aligned to its flight attitude perpendicular to the orbital flight path. Because of the increased mass of the station in this configuration, this maneuver could take up to 30 minutes. Other modules are added to the station in the same manner. Smaller safety exits are provided between the permanent modules. Once the cargo module is added and the 6-man crew is aboard, the modular space station has reached its initial operational capability. Special research and applications experiment modules are added and changed as required by the mission program. The modular space station is capable of maintaining a local vertical hold or an inertial hold flight mode. This provides a stable platform for observing the Earth, Sun, and other astronomical bodies. The cruciform or cross-shaped layout of the station provides maximum stability at minimum fuel consumption as well as structural strength. Modules can be attached without use of the manipulator. Here, a special applications module is docked directly to the core. The station can also be expanded by the addition of another core and modules to hold 12 crew members rather than its initial crew of 6. It is envisioned that this crew would be international in character. The station's facilities would be available to any nation with a legitimate need. Its habitability features are very Earth-like, and both male and female crew members are expected. The station's designed usage flexibility would be such that many different scientific and engineering experiments could be carried out.
Okay, per your request, I'm zooming in now. And it looks like there's a factory at that river junction that's putting something into the air. It shouldn't be. You might have the local pollution boys check that one out.
The space station would provide an overview to assist in the long-term management of the environment. From space, we can observe the overall patterns of air and water pollution. The station could be used to scan an entire continent in an extremely short time, in the neighborhood of 15 minutes. In the view of some experts, we can never have an effective pollution control system until we achieve this viewpoint and ability using both manned and unmanned spacecraft. This same perspective with proper sensing instruments can be used to locate new sources of raw material. Techniques are being developed and tested to locate and diagnose plant diseases, a technique that may actually be easier from space than on Earth, since the sample observed is so large. Today, limited use of these techniques is already saving farmers from huge crop losses. Tomorrow, if, as has been predicted, there will be only 1.4 acres of agricultural land to feed each person, assisting farming of land and sea from space may be a key factor in the survival of a large segment of our population. New and sophisticated methods of weather forecasting will save billions of dollars per year. Already, the comparatively crude weather satellites are showing us how important this overview can be. While some experiments view our Earth, others look outward to the stars and our sun. Studies of the sun from beyond the atmosphere provide vital clues to the workings of this energy producer of the solar system. These studies may hold a clue that would help avert what many experts think could be a future energy crisis on Earth. New materials will be developed and purer materials made aboard this station that could revolutionize the efficiency of their usefulness on Earth. And the list goes on and on. Biology, medicine, physics, even in the field of sociology, long-range trends could be observed, such as what is the effect of man on the areas he inhabits. Once the station is built, the cost of maintaining it will be quite low, while the applications to which it can be put and the benefits derived are virtually unlimited. In our ability to utilize space for the benefit of all mankind may lie the key to a better life on this good Earth.